Hello, everyone. This is Billy Younger, and I thought I'd work a little bit today by showing you a first law thermodynamics problem, basically a calorimetry problem. But remember, the first law of thermodynamics just says that energy cannot be created nor destroyed. It can be transferred, of course, and transformed, I should say. Of course, it can be sent from one object to another and transformed from mechanical energy to heat energy to thermal energy, which is another form of heat energy, that sort of thing, are actually the same form. But it can't really just completely be destroyed. Of course, when Einstein came along, he made it mass energy. So mass energy cannot be created nor destroyed, which means that matter can become energy and energy can become matter. But that's it. So in today's exercise, I'm going to basically just show you how to use a calorimetry or how to solve a calorimetry problem involving a big vat of tea and the ice cube, a large ice cube, and we're going to actually use that to calculate the final temperature of the vat of tea after the big ice cube is added. So let me start off by sharing my screen so you can see the actual question. So here's a question. A stainless steel iced tea dispenser is filled with 4 liters of freshly brewed tea, but strong, sweet tea at 98.0 degrees Celsius. So what I'm meaning is basically, yeah, it could use a little watering down, but it's also still hot, 98.0 degrees Celsius, which of course, you do boil the tea. So that's why it's 98. Then a 2 kilogram block of ice at -6 degrees Celsius is lowered into the tea, which is then allowed to sit for an hour or so before the customers enter the store to purchase tea and other things. A, how many joules and calories, meaning I'm asking you for both answers, will be reached to bring the ice block to a temperature of 0 degrees Celsius? How many joules and calories will be required to melt the entire block, the entire 2 kilogram block? And C, how many joules and calories would it take to bring the 4 liters of tea, which is essentially water, down to 0.0 degrees Celsius? And then finally, assuming no energy lost from the iced tea dispenser, what will the final temperature of the tea be, the final temperature of the tea? So that's the real question. I want to take a moment to write down the data. I know, for instance, that the mass of the tea is actually equal to 4 point, or actually this is not the mass, this is the volume of the tea. Sorry about that. Volume of the tea is 4.00 liters. Of course, the density of water, since tea is essentially water, the density of tea and therefore the density of water is about 1 liter per kilogram. So it's also 4 kilograms. The temperature initially of the tea, so T0T, is equal to 98.0 degrees Celsius. The mass of the block of ice, so I'll say M ice, that's equal to 2.00 kilograms. The initial temperature of the ice, 0 ice, is -6.0 degrees Celsius. And that's about it. So what we're going to do is calculate how much heat is required to bring the block of temperature, the block of ice down to a temperature or up to a temperature of 0 degrees Celsius, how much energy it's going to take to melt it. And then, so A, ice to 0. B, I'm wanting to know ice to liquid. And then C, I want to know how many joules and calories will be required to melt, or excuse me, C, how many joules and calories will it take to bring the iced tea to 0 degrees Celsius. So C, T to 0 degrees Celsius. And then finally, part D, I'm wanting to know final temperature of the tea. Okay, so now I've written down all the information I'm given as well as what I'm asked for so that I hopefully won't forget. Let's stop sharing the screen. Of course, you can do a screenshot if you'd like, or you can pause it and write it down, whatever you want to do. Of course, these documents are also available to you if you just email me at billy@physicssolutions.com, as it says in the notes. So now let's get started on actually solving this problem. So there's a couple different ways you can go about solving a calorimetry problem. The more traditional way, or the way that I see most people doing it, I don't really care for very much, And that just means they'll say delta Q is equal to 0. So what they mean by that is if you add up all the gains and losses of heat in the system, if it really isn't a calorimetric system where you can basically block any loss of heat to the environment or any gaining of heat to the system from the environment, then the total exchange of heat has to add to 0. So all the parts are going to give heat to each other, but not out to the outside world. The problem with that is when you use phrases like Q equals ML for the heat of vaporization, or MLV, well, excuse me, MLV for heat of vaporization, MLF for heat of fusion, so on and so forth. Sometimes students get a little confused as to which one's a positive and which one's a negative. So when you do this, you got to be very specific about what signs there are. You always got to use delta T is final minus initial, so on and so forth. So I generally don't like doing that just because it leads to some errors and the students making some careless mistakes. So what I normally do is I say heat lost equals heat gained. And then by doing that, I just make sure all the heat exchanges are in fact positive quantities. So instead of using delta T equals T final minus T initial, I'll use delta T equals the bigger T minus the smaller T. That way I always get a positive. So what I'm going to say here is that I'm going to say in part A, they want to know basically how much energy, how many joules and calories of energy will it take to bring the ice from negative 6 degrees Celsius to 0 degrees Celsius. I really should write that 0.0 degrees Celsius. So that's part A. So I'm just going to, and the reason why I'm doing this, by the way, you could just solve the problem where you dump the vat of ice into the, or the big block of ice into the vat of tea and find out what the final temperature is. But if you do it that way, there's some problems that you could run into. Like you might assume that there's plenty enough ice to bring the thing down to a certain temperature, but in fact, there might not be enough ice to even bring it down to a certain temperature. So if that's the case, then you could sort of overcalculate. Also, there could be a problem where you might think there's too little ice, and then, of course, or you might think there's more ice than there is, or more ability to do something than there is, and what could happen is the ice would never melt. All those different things cause problems. So what I'm doing is walking it out step by step. I'm going to say, first, let's see how much heat it takes to actually bring the ice from negative 6 degrees Celsius to 0. If that's comparable to the amount of temperature or the amount of heat that is required to cool the tea down to 0 degrees Celsius, which is our ultimate goal if it's really supposed to be a quote-unquote iced tea, then I'm good. Then the next thing is we'll probably find that that's not nearly enough heat to be taken away from the hot tea to cool it down. So then I'll say, well, what about converting it to a liquid from a solid? Is that enough heat? Because what could happen is maybe it does take all this heat, but it doesn't take all the heat that it's required to melt the ice cube, in which case the temperature of the water or the tea, which is acting like water, would be 0 degrees Celsius, and there'd still be some ice left. I wouldn't know that unless I've done this calculation first. So that's why I'm really doing this calculation. And then finally, I'm doing the calculation of what it takes to bring the tea down to 0 degrees Celsius. And if I find that that number is in fact smaller than the sum of these two, then I know it is going to be brought to 0 degrees Celsius, and I can use the system that way. If I find it's bigger, then I know that basically all this is going to happen. In other words, the entire block of ice is going to reduce to or increase to 0 degrees Celsius. Then the entire block of ice is going to melt, and then the entire 2 kilograms of ice, or excuse me, of water that used to be ice, is now going to start cooling the tea, and I can set the final temperatures for both of those equal to each other, and just call it TF and solve the problem. So that's really why I'm doing this. So let's first off calculate the heat required to be added to the ice to bring it up from negative 6 degrees Celsius to 0 degrees Celsius. So I'll say Q, and I'll say ice from negative 6 to 0. That's going to be just MC delta T. But again, I'm using all positive quantities, so I want to make sure I actually do the big temperature minus the small temperature. And the big temperature here would be 0 degrees Celsius. The small temperature would be -6. That is final minus initial, so it all works out okay in this particular case. For the ice, though, of course, the mass is 2.00 kilograms. So if I wanted to work it out, for instance, in joules, I could use 2.00 kilograms. And then I could use the specific heat of ice, which is in fact 2100 joules per kilogram Celsius degree. So 2100 joules per kilogram Celsius degree. And then I'm going to say 0 minus -6.0 degrees Celsius. And doing that math, I've actually worked it out before, but a second calculation can't hurt me. So I'm going to say 2 times 2100 times 6. And that should actually bring us to 2 sig figs. I'm going to carry an extra. I'm going to say that's 25.2 times 10 to the third joules. Now that's carrying 1 extra sig fig because really I should have only had 2 sig figs there. Now I could just convert this to calories to get the other part of the answer, but I could also use the fact that Q ice from -6 to 0 is also equal to 2,000 grams times, now I'm going to take the specific heat of ice in calories per gram per Celsius degree, which is 0.50 calories, that's lowercase c by the way, per gram per Celsius degree, times 0 minus -6.0 degrees Celsius. And in this case, I should get, multiplying it out again, to 2,000 times 1 times 6, obviously, or excuse me, times 0.5 times 6. And that gives me 200. Make sure I did that right because for some reason I was getting a different figure earlier. Oh, okay, gotcha. So that's basically 6,000. 6.00 times 10 to the third calories is the right answer. If you check this, if you actually multiply this by 4.186, you will find that, in fact, that is essentially that number. So that works as well. So we've now done part A. It evidently takes about 25,000 joules, or it takes about 6,000 calories of energy to actually heat the ice, the 2 kilogram cube of ice, up from -6 degrees Celsius to 0 degrees Celsius. Now B, if I want to actually melt the ice, which is really what I'm trying to do here, I have to use the heat of, if it was vaporization, then I would be talking about either going from steam to liquid or from liquid to steam. But in this case, I'm going from liquid to, or excuse me, from solid to liquid. Of course, if I was going liquid to solid, I'd still use the same value, and that's the heat of fusion, not the heat of vaporization. So heat of fusion, or the latent heat of fusion, which is why we use the symbol L, excuse me. So the Q in this case for ice to liquid, okay, that's just M times L fusion. So when we actually do this calculation, if we want to do it for the joule value, then I'll say 2.00 kilograms of ice times the specific, or excuse me, the latent heat of fusion of ice, which is 333. Now in this case, that would be kilojoules per kilogram, which is the same thing, by the way, as joules per gram. So kilojoules per kilogram. So this kilogram and this kilogram is going to cancel out, and that'll give me actually the answer in kilojoules. And I think you can see that that's going to be 666 times 10 to the third kilojoule, or excuse me, times 10 to the third joules. Okay, and this is actually all 3 sig figs, so that's certainly fine. Now again, I could just convert that to calories and do the same thing, but instead I'm going to make use of the fact that it's useful to know the caloric figure as well as the joule figure. So again, I'm going to use MLF, This time I'm going to use 2,000 grams, and I'm going to use the heat of fusion, the latent heat of fusion in calories per gram. That's 79.7 calories per gram. And when I do that math, that turns out to be 159.4. This case, I actually did keep an extra sig fig, times 10 to the third. Calories, again, lowercase calories. If you multiply this times 4.186, then you will obviously get the joule figure that I have up here, at least close enough. So this is the answer to B. 666 kilojoules are 159 calories, 159,000 calories to bring the ice from the solid state to the liquid state. Now, what really matters is if I add this figure and this figure, or this figure and that figure together, that's the total amount of heat it's going to take to bring the ice down to 0 degrees Celsius. That might actually be enough heat that has to be absorbed to actually cool the ice down from 98 degrees Celsius, the tea down from 98 degrees Celsius to 0 degrees Celsius. We just don't know. So that's why I'm calculating part C. And part C is basically how much energy does it take to change the tea from 98 degrees Celsius down to 0 degrees Celsius, which is our ideal scenario, because then we'd have truly iced tea. So in the case of tea, I'm going to say tea from, let's say 98 to 0, and I'll just mark it like that. That's going to, in fact, be the mass of the tea times the specific heat of water, because tea is, basically essentially water, and then times, again, delta T, but this delta T I need to make final minus initial not necessarily be the gold standard for delta. I just want to make sure it's positive. So if it's positive, I actually have to have the big number minus the small number. And of course, the big number is the initial temperature for this one, which is 98, and the small number is 0. So I really need to make sure I do it in the opposite order. So in this case, we actually have 4.00 liters of tea, but the 4.00 liters of tea, since the density of water is 1 kilogram per liter, we know that's also 4 kilograms of tea. So I'm going to write 4.00 kilograms of water times the specific heat of water, which in the case of calories is 4,186. 4,186. So when I go to do that, I'll say 4 kilograms times 4.186. And that's joules. Actually, that's kilojoules per kilocalorie if I wanted to. Actually, no, I think that is, yeah, if I wanted let me double check my figures. If I wanted the actual joules per kilogram Celsius degree, that turns out to be 4,186. So I shouldn't put a decimal place there. It should just be that. So 4,186. And that's going to be joules per kilogram Celsius degree. And then, of course, the temperature change is going to be 98 minus 0, not 0 minus 98, just to keep it positive. So I'm going to say 98.0 minus 0.0 degrees Celsius. Of course, when you subtract them, that makes it Celsius degrees. So that's why the degree comes after. That's sort of the rule that we use just to make things nice and neat. So when I multiply this, I should get 4,186 times 2 times 98, and that should give me 820.5 times 10 to the third. 820, and I'll call it 0.46 times 10 to the third. And I did that just because there might be some ambiguity as to whether this was a 4 or a 5 beforehand, so you'd end up rounding it twice. So it's better to carry 2 digits than to leave that as a 5 and think that I'm going to have to round that up as a 1. So this is 10 to the third, and that unit comes out, of course, in joules. And both of these digits right here are not true sig figs. Again, I can do the same thing for T from 98 to 0. but this time I will use calories, and that is 2,000, or excuse me, 4,000 grams. Dang it, I did 2 again on that, didn't I? Let's see, did I use 2 or did I use 4? I was supposed to do the entire thing of water. So let's check this real quick. I just want to double check. It looks like I actually did, yep, that's what I did. I did the 2 kilograms, which is the mass of the ice. So this answer is not correct, okay? So the actual answer should be 4 times 4186 times 98, and that gives me 1.641. One extra sig fig there, 1.641 times 10 to the 6 joules is what actually comes out there. So that's actually the correct answer. And you can tell that's about twice as big as this, which is what happens when I multiply by 2 instead of by 4. So now I'm going to do the same thing here, 4,000 grams. I'm going to multiply the 4,000 grams times 1.00 calorie per gram Celsius degree times 98.0 degrees Celsius minus 0.0 degrees Celsius. Again, when you subtract those, it becomes Celsius degrees. So when I do this as a 4,000 times 1 times 98, and in this case, I get 392 times 10 to the third calories. 4,000 times 1, 392 times 10 to the third. What did I do on the other one? 4 times 4,186 times 98. Everything looks fine. So this is 392.0 times 10 to the third calories. Now, if I multiplied that times 4.186, of course, that should be the equivalent number of joules, and I get to 1.64 times 10 to the 6. So that does work. Okay, so I was worried because it looked so much different, but anyways, that's just 1 times 1.6 times 10 to the 6, whereas this is 0.4 times 10 to the 6. So it's not as far off as you think. So now I've got that it's going to require basically 1,641,000 joules or 392,000 calories to bring the tea from 98 degrees Celsius to 0 degrees Celsius. So clearly, if you look at this 392,000, if I compare that to the 159,000 plus the 6,000, obviously I'm looking at about 165,000. So that's not nearly enough calories to be burnt, and melting the ice and bringing the ice up to 0 degrees Celsius to get this anywhere near what we need. So what we're going to do is basically assume that what's going to happen is the ice is going to gain heat and the tea is going to lose heat. So the way I will mark that for part D is I'm going to say heat loss equals heat gained. And you could say heat lost, L-O-S-T, equals heat gained. That will work as well, but I'm just writing heat loss. Okay, so if I do that, what I'm going to do is I'm going to say the basically the mass of the tea times the specific heat of the tea, which is really the same thing as water. And this time I'm going to remember the heat, the actual tea is cooling down, so the final temperature will actually be lower than the initial temperature. Since I'm using this method of heat loss equals heat gained, I need that to be positive. So I'm really going to take the initial temperature minus the final temperature. So I'm going to do times 98.0 degrees Celsius minus T final. So this is the thing giving off the heat. This is the heat loss. The thing that's going to gain heat is the ice. And what's going to happen is the ice is going to suck up, let's say, 6,000 calories. And it's going to do that just because what we found earlier was 6,000 calories is what it's going to take to bring it from -6 degrees Celsius to 0 degrees Celsius. So I've got that. Plus, I have that it's going to gain 159.4 thousand. So I'll say plus 159.4 times 10 to the third calories. That's for it to actually melt. And then the rest is going to go to taking the tea that was the ice that was formerly ice and is now just water at 0 degrees Celsius and bringing it up to this new final temperature. This new final temperature, of course, will be higher, so I'll do T final minus it. So now I'm going to say plus the mass of the ice times the specific heat of water this time, because now it's actually already converted to a liquid, times T final minus, in this case, we're starting at 0 degrees Celsius, so 0.0 degrees Celsius. So all I have to do is basically figure out what this quantity is, and then get the T finals on one side and the other stuff on the other side, and that'll ultimately get it for me. So when I multiply the 4,000 times 1 gram times 98, I end up getting 392,000 calories. That's basically 4,000 times 1 times 98. Now minus, if I take the 4,000 times 1, I get 4,000, and that's calories per Celsius degree times T final. That's the left-hand side. The right-hand side, on the other hand, is going to be the 6,000, and I'll call this and this doubtful digits. It's the 159,400 calories. And then finally, our last answer, notice this would be 2,000 times 1 times 0. I get nothing for that, but instead I get plus 2,000 calories per Celsius degree T final. So all I got to do is add this 4,000 to this 2,000 to get 6,000, and then take this 392,000, subtract from it 6,000, subtract from it 159,400, and then divide that answer by 6,000, and that'll give me the T final. So when I do that, I would say 392,000. I'm going to subtract 6,000, and I'm going to subtract 159,400. And I get 226,600. So 226,600 calories is equal to, now I get 6,000. The digits here are what? There should be 3 of them, so I'll call that one doubtful. And that's calories per Celsius degree T final. So I divide both sides by 6,000, and that should give me a final temperature of 37.8 degrees Celsius. And since that had 3 sig figs and this had 3 sig figs, that is actually right to proper number sig figs. The answer was 37.77. So I correctly rounded that to 37.8. So that'll be the final temperature of the tea. Not ideal. In fact, if you're the company wanting to sell the tea, you probably want that as close to 0 degrees Celsius as possible. And 37.8 is not it. Remember, 40 is about a 30 is what, 84 degrees. So that's still pretty darn warm. You don't really want it at that temperature. Maybe you should make instead 2 liters of tea, super strong, and then add 3 kilograms of ice, and then that might actually come closer. So anyways, that's a calorimetry problem. That is also a first law of thermodynamics problem because really we're showing that energy cannot be created nor destroyed. And in fact, we took into account not only the change in temperature due to specific heats, but also the energy that must be transferred to cause a change of state. Again, whenever you're changing a state, if you're going from, for instance, from a solid state to a liquid, you have to add heat to that solid to make it break loose the atoms that are attracted to one another. That heat required is basically the mass times the latent heat of fusion. If you then go further and try to take that liquid and convert it to a gas, you've got to further break the energy, bonding the liquid atoms together, the atoms of the liquid together, and that's the latent heat of vaporization that you would use. Again, you've got to add heat to go that way. Going the other way, you got to take away heat. That's where the negatives come in if you tried to use the delta Q equals 0. So I hope that helps you see how to solve a calorimetry problem. Here, just in case the image isn't that great, I'll scan over this so you can see the writing. Don't forget I did make a boo-boo there and used my number for 2 kilograms instead of for 4 kilograms, but ultimately fixed it, and that gave us a final temperature for the T of 37.8. And hopefully that step-by-step process helped you understand why we had to do it the way we did. Have a good day.